Alright, so now we're going to talk about what shape these are in 3D space. What do molecules actually physically, like how do they orient themselves? What do they look like? And I'm going to say right off the bat, so there's a 3D modeling tool I'm going to link in the kind of supplementary materials, the extra stuff at the bottom of the page. And I encourage you to use that tool to make some of the molecules, or ideally all the molecules I'm going to talk about in this section. And the cool thing is you'll be able to rotate them and you can look at them in 3D. So on paper, what I'm going to do is I'm going to show you how we draw 3D representations, and it is not exactly awe-inspiring. So the ability to 3D render is much better. So, and the cool thing is you can kind of follow along. So just kind of like split screen it or whatever. Use that link, launch that tool, and make these molecules and see what they look like, and then you can kind of augment what I'm talking about here. So what this is built on is, again, the name is very descriptive and not at all creative, but this is valence shell electron pair repulsion theory. Oops. And you know chemists aren't going to say that. We call it Vesper theory. We're not saying valence shell electron pair repulsion theory. Oh, you got to breathe in the middle. We are just going straight Vesper. So, and it's, yeah, it looks like something that James Bond would be fighting against, right? Some sort of organization. But it is valence shell electrons that pair up and repulse each other. That's what they do. I mean, the name really, it is all in the name. Okay, so let's kind of distill this down a little bit, though. So I think I've made the point here. It's been a few weeks now, but electrons really don't like each other. All right, they're both the same charge. They don't get along. They fight like alley cats, whatever. You know. And so these bonds create areas where there are two electrons in the area and they get along well enough. But if you have two areas with electrons, they're going to try to get away from each other. They're going to repel each other. And so if you have two areas with bonds, they're going to repel each other. If you have an area with a lone pair and a bond, they're not going to want to be right next to each other. They're going to try to get as far away as possible. And so I'm going to call them areas of electron density, but that just means like a bond or a lone pair. So areas of electron density, i.e. bonds and lone pairs, get as far from each other as possible. I definitely wrote this definition. It's not hard to tell when I write one and when I just steal it out of the book or off of like Wikipedia or something, because I definitely use very, very casual language. Okay, so again, we're just going to jump in with an example. We're going to break it down. We're going to diagram it. Okay. So I've sort of tipped my hand a little bit in terms of talking about this stuff, but let's get it in writing. CH4. Well, here is our electron dot structure for CH4. And here, little loopy arrow, you know something fancy's coming when I draw that arrow, is our 3D representation. What did I just do? Okay, well, all of these are chemical bonds. Whether they're a line, a dash, or a wedge. I'll make this wedge a little bit wider so it's a little bit clearer on the there we go, on the camera. Looks good. Camera makes all wedges 5 pounds slimmer. Everyone knows that. So, here's what we're looking at. I've got carbon as my central atom, just like I do over here. And then this hydrogen and this hydrogen right here. And they are flat on the surface. So if my carbon is flat on the surface, this hydrogen is flat above it. This hydrogen is angled off to the side like so. Well, where's this hydrogen? Well, it is bumping out towards you. And then this one is going into the paper. It is behind it. And so what we have is, remember, this is in 3D space. So there are 4 areas of electron density. There are 4 single bonds. They are all trying to get away from each other as much as possible. And what that does is it creates a situation where they are 109.5 degree bond angles. So this guy and this guy, they're flat on the paper between them, right here, 109.5 degrees. Guess what the bond angle is between these two? 109.5 degrees. If I pivot it around, I get the same angle. And so they get the same angle between all the hydrogens. So they are spread out away from each other as far as possible. And the name for this shape is tetrahedral. And so tetris is a bunch of 4 piece blocks that you're stacking together. So tetra means 4. That's where the name Tetris comes from. And then hedral because, I don't know, it's tetrahedral. I don't know. Latin probably. Hopefully not Greek, because then, you know, my grandmother would be so disappointed in me for not knowing that. And so this is a tetrahedral shape. Okay, so what else is there to say about it? Yeah, they're just orienting away from each other as much as possible. So as the number of electron groups change, our geometry can change, but also there's one more detail on top of that. So all 4 of these groups are bonds. There are no lone pairs here. Lone pairs, they're like balloons. Bonds they're like those balloons that you can turn into, like, you know, you fold it up and make like a wiener dog or whatever. These are like party balloons. They're like balloon shaped, not tube shaped. They're balloon. And so they spread out a little bit more. And so when there are bonds, they tend to crunch the bond angle a little bit because these big balloons are inflating and pushing down. They're forcing our bond angles to shrink between bonded groups. So these lone pairs spread out more. And compress the bond angles. So let's look at NH3. This is ammonia. If your neighbor has too many cats, you know the smell. If you have too many cats, your neighbor knows the smell. So, it is going to be like so. That is our electron dot structure. And then our lone pair, I'm going to put the lone pair in the back. So those are our 2 dots, that's our lone pair. So it has 3 hydrogens bonded. Now it would be 109.5, except this lone pair is going to push these bonds closer together. So you've got these bonds, right? And they're going to try to get away from the lone pair. They're going to squeeze in a little bit. They're going to squeeze in away from that lone pair. Lone pair is going to take up space. Like, it is like an inflating balloon. It's going to push everything out of its way a little bit. And so it squeezes this bond angle down to 107 degrees. So the lone pair pushes the bonded groups closer together. So that's what we're seeing. And so that angle shrinks a little bit. And so there's a name for this shape. So this is tetrahedral. You know, it's four bonded groups. Forgot to mention that earlier. Okay. Over here we have trigonal pyramidal, because it looks like a three-sided pyramid when you stack it. Can I fit pyramidal there? I'm going to go for it. Oh, that was a bad idea. Oh, I did it. Oh, whew. Living on the edge. Okay, and so this is 3 bonded groups plus 1 lone pair. You've got 1, 2, 3 areas where there's bonding and 1 with a lone pair. And that's going to get you trigonal pyramidal, which is going to have a 107-degree bond angle. Okay, so what else can we say about this? Well, more lone pairs equals more compression. We're going to bring our old friend Superstar back into this now. H2O. You guys have seen this structure a few times now. Okay. Well, here's what it looks like in 3D. Lone pair there. Lone pair there. So it's like so, but those lone pairs are going to squeeze this together even more, and so it's going to be even less than 107. It's going to be 104 degrees, or sorry, 104.5 degrees. And the name for this structure, no joke, it's bent. I wish they'd gone with boomerang. Boomerang would have been so cool. They went with bent, which makes it sound like there's something like water is like got broken, like it's like a bent pipe or something. But that's, you got 2 bonded groups plus 2 lone pairs. All right. And so again, you have 2 lone pairs instead of 1 like on ammonia, and that bond angle gets squeezed even more. Just keep squeezing and squeezing. So, there's a couple other geometries to talk about. There's a few beyond these, but these are the only ones I expect you to know right now. You've got something like HCl. I'm not even going to draw the 3D representation. It's going to be 180 degrees, right? Like you can't bend the bond itself. The bond is going to be like a straight area of space, and so it's just going to be flat. And so we call this linear if you have 2 atoms. So if you only have 2 atoms, automatically linear geometry, 180 degrees. You can also have something like CO2. So you have oxygen double bonded to carbon, double bonded to oxygen. Well, that is the 3D representation. It too is 180 degrees. It is also linear. These are going to get as far apart as they can. Well, how do you get as far as possible? There's only 2 groups, North Pole, South Pole. There you go. You just get away from each other. And so in this case we have 2 bonding areas only. So even though they're double bonds, this is one region of electron density. This is one region of electron density. It's not about the number of bonds because they're all going to occupy this space. It's just where are they? So it's not like I can split this up. Like it has to be between the carbon and oxygen. This has to be between this carbon and oxygen. And so it's just going to orient with the oxygens. So they're going to get as far apart as they can. So it's essentially 2 groups. So a lot of students get tripped up by that. But it doesn't matter if it's a double, triple bond, single bond. It's one area of bonding density. Or electron density that just happen to be used for bonding. All right, and then one more, and this is another one that is a good example that your book stole from me, even though I'm sure the book was written before I was doing this stuff, but that's beside the point. So we can have something like this. And so what we have, as you can clearly see, is 3 areas all bonding around a central atom. So we have 3 areas of electron density. We got 1, 2, 3. And so what does this look like? In 3D space, it's going to be flat, and it's going to be spread out as much as possible. If one of them were to get out of the flat plane, it would be closer to the other ones than if it stayed flat. So it stays flat, and you get 120 degrees. Take 360 degrees, divide it in 3, you get 120. And this is known as trigonal planar. And so this is 3 bonding areas. No lone pairs. Alright, so your book has a kind of wonky table of geometries. You can look up and see that there are more. What I'm showing right now is only for a normal octet, so everything I've shown means the central atom has 8 electrons around it. I can't really get around hydrogen is only having 2. That's known as a deficient octet, but what I'm not showing you is an expanded octet. So there's groups that have like 5 or 6 bonds. It gets up to 8. It's a mess. So, well, actually, doesn't. No, it just gets up to 6. Excuse me, I misspoke. But yeah, but it is a mess. But we're not going to go beyond just the normal 4. So these are all the geometries I expect you to know. I expect to know the bond angles and the names, and to be able to determine them. Really based just on, you don't need to draw the 3D structure. These were just for demonstration purposes. But if you look at this, you should go like, oh, I've got 2 areas with bonding 2 lone pair, 2 bonding 2 lone pair. Oh, it's a bent geometry. It's 104.5 degrees. That's what I expect you to be able to do. And you know, I'll have a practice worksheet that will kind of help frame the strike zone and this stuff. If you do watch other videos on electronic geometry and molecular geometry, you're going to get a lot more information than I've shown you, and I don't expect you to know more than what I show you, so just a heads up on that. Alright, so we got one more topic this week, and so we are going to take this idea of geometries, and we are going to mix it with the idea of polar bonds and non-polar bonds from before, and we're going to talk about polar molecules. So we're going to take that idea and we're going to scale up. So we actually have to fold 2 subjects we just talked about this week to be able to discuss the last one. So it's a good thing I did that one last, or it would have been really confusing, right? So yeah, one more to go, and then that'll be it.